students, welcome to our YouTube channel Experience Tutor. Today we'll discuss class 12 physics, moving charges and magnetism. Chapter 4 NCERT solution part 3. Our mission is to provide free classes on YouTube for all the students of class 6 to class 12. And for the students who are preparing for IIT, JEE, NEET, NDA and other competitive examinations. Before we begin, we have a small request. Please subscribe, like and share our channel. Please click on the subscribe button to support us and also click on the bell icon to get automatic notification whenever a new video is uploaded by us. Let us begin today's class. In the last class, we have done till problem number 4.16. In today's class, we'll start with problem number 4.17. A toroid has a core non-ferromagnetic of inner radius 25 centimeter and outer radius 26 centimeter, around which 3500 turns of a wire are wound. If the current in the wire is 11 ampere, what is the magnetic field? A. Outside the toroid, B. Inside the core of the toroid, and C. In the empty space surrounded by the toroid. Let us see the solution. Here we can see inner radius of the toroid R1 is equal to 25 centimeter, which is equal to 0.25 meter. Outer radius of the toroid R2 is equal to 26 centimeter, which is equal to 0.26 meter. Number of turns of the coil N is equal to 3500. Current in the coil I is equal to ILA. Current in the toroid is equal to I is equal to 11A. Magnetic field outside the toroid is 0. It is non-zero only inside the core of the toroid. Magnetic field inside the core of a toroid is given by the relation B is equal to mu naught N I upon L, where mu naught is equal to permeability of free space is equal to 4 pi to the power multiplied by 10 to the power minus 7 TMA minus. L is equal to length of the toroid is equal to 2 pi R1 plus R2 upon 2. So putting the value of R1 and R2, we get pi 2 bracket 0.25 plus 0.26, which is equal to 0.51 pi. B is equal to, therefore B is equal to 4 pi multiplied by 10 to the power minus 7 multiplied by 3500 multiplied by 11 upon 0.51 pi, which is approximately equal to 3 multiplied by 10 to the power minus 2 t. C. Magnetic field in the empty space surrounded by the toroid is 0. Let us see the next problem. Now we'll solve problem number 4.18. Answer the following question. A. A magnetic field that varies in magnitude from point to point but has a constant direction east to west is set up in a chamber. A charged particle enters the chamber with and travels undeflected along a straight line with a constant speed. What can you say about the initial velocity of the particle? Let us see the solution. So 18a, the solution is the initial velocity of the particle is either parallel or antiparallel to the magnetic field. Hence, it travels along a straight path without suffering any deflection in the field. Let us see B part. Part B, a charged particle enters an environment of a strong and non-uniform magnetic field varying from point to point both in magnitude and direction, and comes out of it following a complicated trajectory. Would its final speed equal an initial speed equal the initial speed if it suffered no collision with the environment? Let us see the solution. Yes, the final speed of the charged particle will be equal to its initial speed. This is because magnetic force can change the direction of velocity but not its magnitude. Let us see the next problem. So, let us understand the problem. A charged particle enters an environment of a strong and non-uniform magnetic field varying from point to point both in magnitude and direction. So, magnetic field is varying from point to point both in magnitude and direction. Okay. And comes out of it following a complicated trajectory. Would its final speed equal the initial speed if it suffers no collision with the environment? Okay, now let us see the solution. So, yes, the final speed of the charged particle will be equal to its initial speed. This is because magnetic force can be changed can change the direction of velocity but not the magnitude. Okay, good. So since speed is a scalar quantity, so the magnitude will be same for final and initial speed, and velocity, final velocity and initial velocity will be uh, the final speed and initial speed will be same, but final velocity will be different that of initial velocity because it is a vector quantity and it contains magnitude and direction both. And here in the problem it is telling that it is changing its direction to every point. So velocity will be different but speed will be same because magnitude will be same and direction will be different. So now it is clear. Let us move to the next question. So now part C. An electron travels west to east, enters a chamber having a uniform electrostatic field in north to south direction. Specify the direction in which a uniform magnetic field should be set up to prevent the electron from deflecting from its straight line path. Let us see the solution. An electron traveling from west to east enters a chamber having uniform electrostatic field in the north-south direction. The moving electron can remain undeflected if the electric force acting on it is equal and opposite of magnetic field. Magnetic force is directed towards the south. According to Fleming's left-hand rule, magnetic field should be applied in a vertically downward direction. Now let us see the next problem. Next problem is 4.19. An electron emitted by a heated cathode and accelerated through a potential difference of 2 kV enters a region with uniform magnetic field of 0.15 T. Determine the trajectory of the electron if the field A is transverse to its initial velocity, B makes an angle 30° with initial velocity. Let us see the solution. So, magnetic field strength B is equal to 0.15 T. Charge on electron E is equal to 1.6 multiplied by 10 to the power minus 19 coulomb. Mass of electron m is equal to 9.1 multiplied by 10 to the power minus 31 kg. Potential difference V is equal to 2 kV is equal to 2 multiplied by 10 to the power 3 V. Thus, kinetic energy of the electron EV is equal to half mv square. Therefore, B is equal to 2 under root 2 EV by m. This is equation 1, where B is the velocity of the electron. A. Magnetic force on electron provides the required centripetal force of the electron. Hence, electron traces a circular path of radius r. Magnetic force on the electron is given by the relation BeV. Centripetal force mv square is equal to mv square upon r. Now, BeV is equal to mv square upon r. R is equal to mv upon Be is equal to equation number 2. From equation 1 and 2, we get R is equal to m upon Be 2 EV upon m under root, or to the power half. Putting the values of 9.1 multiplied by 10 to the power minus 31 upon 0.15 multiplied by 1.6 multiplied by 10 to the power minus 19 bracket under root or to the power half 2 multiplied by 1.6 multiplied by 10 to the power minus 19 multiplied by 2 multiplied by 10 to the power 3 upon 9.1 multiplied by 10 to the power minus 31, and upon solving we get 100.55 10 to the power minus 5 meter, and upon solving this we get 1.01 multiplied by 10 to the power minus 3 meter, and upon solving we can get 1 millimeter. So the electron has a circular trajectory of radius 1 millimeter normal to the magnetic field. Let us see the next part of the problem. So the B part is telling makes an angle 30 degree with the initial velocity. So this part. Let us see the solution. So when the field makes an angle theta of 30 degree with the initial velocity will be v1. V1 is equal to v sine theta. From equation 2, we can write the expression for new radius as r1 is equal to mv1 be is equal to mv sine theta upon be. Putting the values of mv sine theta, b and e, we get, and upon solving we get 0.5 multiplied by 10 to the power minus 3. Upon solving we get 0.5 millimeter. Hence the electron has a helical trajectory of radius 0.5 millimeter along the magnetic field direction. Let us see the next problem. Now let us see problem number 4.20. A magnetic field set up using Helmholtz coil described in exercise 4.16 is uniform in a small region as a magnitude of 0.75 T. In the same region, a uniform electrostatic field is maintained in a direction normal to the common axis of the coil. A narrow beam of single species charged particle all accelerated through 15 kilovolt kV enters this region in a direction perpendicular to both the axis of the coil and the electrostatic field. If the beam remains undeflected when the electrostatic field is 9.10 to the power minus 5 volt per meter, make a simple guess as to what the beam contains. Why is the answer not unique? Let us see the solution. So, magnetic field B is equal to 0.75 T. Accelerating voltage V is equal to 15 kV is equal to 15 to the power 15 into 10 to the power 3 volt. Electrostatic field E is equal to 9 into 10 to the power 5 volt per meter. Mass of the electron m is equal to m. Charge of the electron is equal to E. Velocity of the electron is equal to V. Kinetic energy of the electron is equal to EV, which implies that half mv square is equal to EV. Therefore, E upon m is equal to V square upon 2V, which is equation number 1. Now, since the particle remains undeflected by the electric and magnetic field, we can infer that electric field is balancing the magnetic field. Therefore, small e multiplied by capital E is equal to small e V by BB. V small v is equal to E by B. This is equation 2. So, putting the equation 2 in equation 1, we get E upon m is equal to half E upon B whole square upon V is equal to E square 2V up E square upon 2V B square. Putting the value of E, V and B we get, and upon solving we get 4.8 multiplied by 10 to the power 7 C per kg. The value of specific charge E upon m is equal to deuteron or deuterium ions. This is not a unique answer. Other possible answers are helium, lithium, helium plus plus, He plus plus, lithium plus plus, Le, Li plus plus, etc. Let us see the next problem. Now let us see question number 4.21. A straight horizontal conducting rod of length 0.45 meter and mass 60 gram is suspended by two vertical wires at its ends. A current of 5 ampere is set up in the rod through the wires. A. A. What magnetic field should be set up normal to the conductor in order that the tension in the wire is 0? Let us see the A part first. Length of the rod L is equal to 0.45 meter. Mass suspended by the wire M is equal to 60 gram, that is 60 multiplied by 10 to the power minus 3 kg. Exertion due to gravity G is equal to 9.8 meter per second square. Current in the rod flowing through the wire I is equal to 5 ampere. Magnetic field B is equal to opposite to the weight of the wire, that is BIL is equal to mg. Therefore, B is equal to mg upon IL. Putting the value of mg, I and L, we get 0.26 T. The horizontal magnetic field of 0.26 T normal to the length of the conductor should be in order to get zero tension in the wire. The magnetic field should be such that Fleming's left-hand rule gives an upward magnetic force. Let us see the B part of the question. What will be the total tension in the wires if the direction of the current is reversed, keeping the magnetic field same as before? Ignore the mass of the wire. G is equal to 9.8 meter per second square. Let us see the solution. So, if the direction of the current is reversed, then the force due to the magnetic field and the weight of the wire acts in the vertically downward direction. The total tension of the wire BIL plus mg. Putting the value of BIL, m and g, and on solving we get 1.176 Newton. Let us see the next problem. Now let us begin with problem number 4.22. The wires which connect the battery of an automobile E to its starting motor carrying a current of 300 ampere for short time. What is the force per unit length between the wires if they are 70 centimeter long and 1.5 centimeter apart? If the force is the force attractive or repulsive? Let us see the solution. So current in both the wire I is equal to 300 ampere. Distance between the wire R is equal to 1.5 centimeter, that is 0.015 meter. Length of the two wires L is equal to 70 centimeter, that is 0.7 meter. Force between the two wires is given by the relation F is equal to mu naught I square upon 2 pi r, where mu naught is the permittivity of the free space, is equal to 4 pi multiplied by 10 to the power minus 7 Tm A inverse. Putting the value of mu naught I and R, and upon solving we get a value of 1.2 Newton per meter. Since the direction of the current of the wire is opposite, a repulsive force exists between them. Let us move to the next question. Now let us see problem number 4.23. A uniform magnetic field of 1.5 T exists in a cylindrical region of radius 10 cm. Its direction parallel to the axis along east to west. A wire carrying current of 7 ampere in the north or to south direction passes through the region. What is the magnitude and direction of the force on the wire if A, the wire intersects the axis, B, the wire turns from north-south to northeast northwest direction, C, the wire in the north-south direction is lowered from the axis by a distance of point of 6 centimeter. Let us see the solution. Magnetic field strength B is equal to 1.5 T. Radius of the cylindrical region R is equal to 10 centimeter, that is 0.1 meter. Current in the wire passing through the cylindrical region I is equal to 7A. A. If the wire intersects the axis, then the length of the wire is the diameter of the cylindrical region, that is length is equal to 2R, that is 0.2. Angle between the magnetic field and the current is equal to theta is equal to 90 degree. Magnetic field acting on the wire is given by the relation Bf is equal to BIL sine theta. Putting the value of BIL and theta we get, and upon solving we get a value of 2.1 Newton. Hence, a force of 2.1 Newton acts on a wire in a vertically downward direction. Let us see the part B. New length of the wire after turning it to the northeast and northwest direction can be given as L1 is equal to L sine theta. Angle between the magnetic field and the current theta is equal to 45 degree. Force on the wire is equal to F is equal to BIL sine theta. BI where putting the value of BIL we get, and theta we get 2.1 Newton. Hence, a force of 2.1 Newton acts vertically downward on the wire. This is independent of angle theta because L sine theta is fixed. Now the part C. The wire lowered from the axis by distance d is equal to 6 centimeter. The Let L2 be the new length of the wire. L2 upon 2 whole square is equal to 4 bracket d plus r, that is 4 bracket 10 plus 6, that is 4 bracket 16, that is 64. L2 upon 2 is equal to under root 64, that is 8. So L2 is equal to 8 multiplied by 2, that is 16, that is 0.16 meter. Magnetic force exerted on the wire F2 is equal to BIL2. Putting the value of BI and L2 we get, and upon solving we get 1.68 Newton. Hence, a force of 1.68 Newton acts in a vertically downward direction on the wire. Let us see the problem number. Next problem. 4 point. So next problem is 4.24. A uniform magnetic field of 3000 G is established along the positive z direction. The rectangular loop of side 10 cm and 5 cm carries a current of 12 ampere. What is the torque of the loop in the different cases shown in figure 4.28? What is the force on each cases? Which case corresponds to the stable equilibrium? And here's the figure 4.28. And let us see the solution. Magnetic field strength B is equal to 3000 G, that is 3000 multiplied by 10 to the power minus 4 T, that is 0.3 T. Length of the rectangular loop L is equal to 10 centimeter. Width of the rectangular loop B is equal to 5 centimeter. Area of the loop A is equal to L into B, that is 10 into 5, that is 50 centimeters square, which is equal to 50 multiplied by 10 to the power minus 4 meters square. Current in the loop I is equal to 12 ampere. Now taking the anti-clockwise direction of the current as positive and vice versa. A, the torque tau is equal to L A cross B. From the given figure, it can be observed that A is normal to the xy plane and B is directed along z axis. Tau is equal to 12 multiplied by 50 multiplied by 10 to the power minus 4 I plus 0.3 K. Upon solving, we get 1.8 multiplied by 10 to the power minus 2 J Newton meter. The torque is 1.8 multiplied by 10 to the power minus 2 Newton meter along negative y direction. The force on the loop is 0 because angle between A and B is 0. Let us see the B part. So in part B, the case is similar to case A, hence the answer is same as case A. Let us see the next part C. Torque tau is equal to IA cross B. From the given figure, it can be observed that A is normal to xy plane and B is directed along the z-axis. R is equal to minus 12 multiplied by 50 multiplied by 10 to the power minus 4 J multiplied by 0.3 K is equal to minus 1.8 multiplied by 10 to the power minus 2 I Newton meter. The torque is 1.8 multiplied by 10 to the power minus 2 Newton meter along the negative x direction, and the force is 0. Magnitude of torque is given as magnitude of torque modulus of torque is equal to IAB, putting the value of IA and B, and upon solving we get 1.8 multiplied by 10 to the minus 2 Newton meter. The torque 1.8 The torque is 1.8 10 to the minus 2 Newton meter at an angle 240 degree with a positive x direction. The force is 0. Part E, torque tau is equal to IA cross B. Putting the value of IA and B, we get and calculating, we get 0. Hence, the torque is 0. The force is also 0. Part F, torque tau is equal to IA cross B. Putting the values, I get tau is equal to 0. Hence, the torque is 0. The force is also 0. In case E, the direction of IA and IB is same and the angle between them is 0. If displaced, they come back in equilibrium. Hence, the equilibrium is stable. Whereas in case F, the direction of IA and IB are opposite. The angle between them is 180 degree. If disturbed, it does not come back to its original position. Hence, the equilibrium is unstable. Let us see the next problem. Let us see problem number 4.25. A circular coil of 20 turns and radius 10 cm is placed in a uniform magnetic field of 1 T normal to the plane of the coil. If the current in the coil is 5 ampere, what is the total torque on the coil? B. Total force on the coil. C. Average force on each electron in the coil due to the magnetic field. Let us see the solution. Number of turns on the circle coil n is equal to 20. Radius of the coil r is equal to 10 centimeter, that is 0.1 meter. Magnetic field strength B is equal to 0.1 T. Current in the coil I is equal to 5 ampere. A. The total torque on the coil is 0 because the field is uniform. The total force B. The total force on the coil is 0 because the field is uniform. B is also the same answer. C. So cross section, part C. Cross sectional area of the copper A is equal to 10 to the power minus 5 meters square. Number of free electrons per cubic meter is in copper is equal to N is equal to 10 to the power 29 per meter cube. Change on the electron E is equal to 1.6 multiplied by 10 to the power minus 19 C. Magnetic force F is equal to BeVd, where Vd is equal to the velocity of the electron is equal to I upon NaE. Therefore, F is equal to BeI upon NeA. Now, upon putting the values and upon solving, we get 5 multiplied by 10 to the power minus 25 Newton, and hence the average force on each electron is 5 multiplied by 10 to the power minus 25 Newton. Now, problem number 4.26. A solenoid 60 centimeter long with a radius 4 centimeter has 3 layers on of windings of 300 turns each. A 2 centimeter long wire of mass 2.5 gram lies inside the solenoid near its center. Normal to its axis. Both the wire and the axis of the solenoid are in the horizontal plane. The wire is connected through two leads parallel to the axis of solenoid to a external battery which supplies a current of 6 ampere in the wire. What value of current which appropriate with appropriate sense of circulation in the windings of the solenoid can support the weight of the wire, that is G is equal to 9.8 meter per second square. Let us see the solution. So length of the solenoid L is equal to 60 centimeter, that is 0.6 meter. Radius of the solenoid R is equal to 4 centimeter, that is 0.04 meter. It is given that there are 3 layers of windings of 300 turns each. Total number of turns N is equal to 3 into 300, that is 900. Length of the wire L is equal to 2 centimeter, which is equal to 0.02 meter. Mass of the wire M is equal to 2.5 gram, which is equal to 2.5 multiplied by 10 to the power minus 3 kg. Current flowing through the wire is I is equal to 6 ampere. Acceleration due to gravity G is equal to 9.8 meter per second square. Magnetic field produced inside the solenoid can be given by the relation B mu naught I Ni L Ni upon L. B is equal to mu naught Ni upon L, where mu naught is equal to permittivity of free space is equal to 4 pi multiplied by 10 to the power minus 7 Tm A inverse. I is equal to current flowing through the windings of solenoid. Magnetic force is given by the relation F is equal to BIL. Putting the value of B, we get mu naught L NL upon capital L multiplied by IL. Also, the force on the wire is equal to the weight of the wire, that is mg is equal to mu naught NIIL upon capital L. Therefore, capital I is equal to mgl upon mu naught NIL. Putting the values, we get 108 ampere. Hence, the electric current flowing through the solenoid is 108 ampere. Let us see the next problem. Our next problem is 4.27. A galvanometer coil has a resistance of 12 ohm and the meter shows full scale deflection for a current of 3 milliampere. How will you convert the meter into a voltmeter of range 0 to 18 volt? Let us see the solution. So, resistance of the galvanometer coil is equal to G is equal to 12 ohm current, for which there is a full scale deflection Ig is equal to 3 milliampere is equal to 3 multiplied by 10 to the power minus 3 A. Range of the voltmeter is 0, which needs to be converted to 18 volt. V is equal to 18 volt. Let a resistance of let a resistor of resistance R be connected in series with the galvanometer to convert it to a voltmeter. So this resistance is given as R is equal to V upon Ig multiplied by G. Putting the value of V, Ig and G, we get the answer as here it will be minus V upon Ig 18. So here R is equal to minus. So upon solving, we get 5988 ohm. Hence, the resistor of the resistance 5988 ohm is to be connected in series with the galvanometer. Let us see the next problem. The next problem is 4.28, which is the last problem of this exercise of lesson 4, chapter 4. A galvanometer coil has a resistance of 15 ohm and a meter shows full scale deflection for a current of 4 milliampere. How will you convert the meter into a meter of range 0 to 6 ampere? Let us see the solution. So resistance of a galvanometer coil G is equal to 15 ohm. Current for which the galvanometer shows full scale deflection Ig is equal to 4 milliampere, that is 4 into 10 to the power minus 3 ampere. Range of the emitter is 0, which needs to be 6 ampere. The current I is equal to 6 ampere. A shunt resistor of resistance S to be connected in parallel to the galvanometer to convert into ammeter. The value S is given by S is equal to Ig G upon I minus Ig. Putting the value of Ig, G, I and Ig and solving it, we get 0.06 upon 5.996, which is approximately equal to 10 milliampere. Hence the shunt resistor is to be connected in parallel with the galvanometer. So this is the end of today's lesson. Before we close our class, we have a small request. Please subscribe, like and share our YouTube channel among your friends and relatives. Please click on the subscribe button to support us and also click on the bell icon to get automatic notification whenever a new video is uploaded by us. Thank you for watching our videos and supporting us.